You'll want to be able to draw the mechanism for the sulfonation of benzene. That's putting one of these SO3H groups onto a benzene ring. And the process is going to have some similarities to the bromination of benzene. And the first step is just the principle behind the reaction. We saw in the video for the bromination of benzene that a benzene itself is a nucleophile. You recognize nucleophiles because they either have a full negative charge, a partial negative charge, a lone pair, or a pi bond. Benzene has pi bonds, so that makes it a nucleophile. But benzene is really, really stable, so it's a poor nucleophile. It's not going to react very well. And the only way we can tempt it to react is by combining it with a really awesome electrophile. Now, in the case of bromination, we had to add a metal catalyst to turn the bromine into a really awesome electrophile. But in this case, we're going to have a really awesome electrophile from the very beginning. Let me show you how this reaction is usually written when somebody doesn't show the mechanism. If they just want to give a sense of the recipe, you have that SO3H, and that usually is done by adding what's called fuming sulfuric acid. So this fuming sulfuric acid is, the fumes are a gas coming from a gas that you're using, and the gas that you use is sulfur trioxide. You can see that if you bubble sulfur trioxide gas through water, you end up getting H2 SO4, which is sulfuric acid. And so if you just bubble sulfur trioxide gas, this SO3 gas, through water a lot, you'll get pretty concentrated sulfuric acid. But in addition to the sulfuric acid, that'll exist in equilibrium with sulfur trioxide gas and water. So you'll have all three of those species present in fuming sulfuric acid. And it's actually the species on the left that are going to be responsible for this next reaction. Let's take a look at that sulfur trioxide. It looks a little bit like this. And hopefully, when you look at this, something might seem a little weird. The sulfur has a whole bunch of electrons around it. It has 2, 4, 6, 8, 10, 12 valence electrons. So it's not following the octet rule. What's happening there? The octet rule is only strictly true for atoms in the second row of the periodic table. It's coming from the fact that you have one s orbital and 3 p orbitals, the px, py, pz. So each of these can hold 2 electrons. So 2 in the s, 2 in the py, 2 in the px, 2 in the pz. That gives you the 8 electrons that those orbitals can hold. In the case of sulfur, sulfur is lower down on the periodic table. It's below oxygen. It's in the third row. And so it has access to 3 d orbitals, to the d orbitals in the third row. And then there are 5 different d orbitals. And they look kind of funny, and I won't spend time drawing them here. You can look up pictures online. They're kind of beautiful. There are other wave patterns for how electrons can move if they have more energy. They have more nodes. But it has extra d orbitals, and that's why it's able to hold more electrons around it than just the regular 8 that it can hold with the s and p orbitals. So that's the first thing that might look confusing with this sulfur trioxide molecule, but that's the explanation for that. Another thing you should notice is you have a lot of bonds to oxygen. Oxygen is really electronegative. I mean, oxygen appears a lot in organic chemistry because the organic chemistry we deal with has evolved on Earth, where there's a lot of water, and so the carbon molecules have been able to react with oxygen molecules a lot, so they get stuck onto the oxygen. So we see oxygen a lot in molecules, and it's really, really electronegative. So of the commonly appearing characters in the supporting cast of organic chemistry, oxygen is the most electronegative. Fluorine is the only element that's more electronegative than oxygen, but it doesn't appear as often. So each of these oxygens is going to pull electrons toward itself and steal electrons from the sulfur. So you can see that the sulfur is an electrophile. Now, because of all of those bonds to oxygens, you have 6 bonds to oxygens, you can imagine the compounding effect of all of that electronegativity. So that, I drew that as just a slight positive charge, but really it's almost a full positive charge. It's a really big slight positive charge because of the different effects of those electronegativity. And there's one other thing that makes that sulfur an incredible electrophile, and that's if you think about the p orbitals, right? The p orbitals that are creating these pi bonds. There's a pi bond. Remember, a pi bond, that's every bond after the first bond you form. There's a pi bond to each of those oxygens. Let's zoom in on just one. I'm going to draw the p orbital for sulfur in purple, and I'm going to draw the p orbital for oxygen in yellow. So these are the p orbitals going to create that orange pi bond. Sulfur is lower, it's in the one row lower on the periodic table. So its orbitals are bigger. Atoms get bigger as you go down. The orbitals, the standing waves that electrons fly in, get larger as you go down on the periodic table. So the p orbital for sulfur is going to be really big, and the p orbital for oxygen is going to be not as big. And so the overlap between those orbitals is not going to be that great. You're just going to have overlap in a couple places, small places, and then of course you have the place where you don't have the overlap in the pi bond, where you have the node, and so that pi bond is really going to be very weak. The electrons will almost entirely stay on the more electronegative atom, which is oxygen. So the pi bonds almost don't even exist. It's almost as if the sulfur is really just singly bonded to these oxygens, and the oxygens are all just hogging those electrons all the time. And the sulfur just has a bunch of positive charge on it. So for both of those reasons, sulfur trioxide is an incredible electrophile. First, because it's bonded to, it has 6 bonds to oxygen, so that's a huge, the electronegativity of the oxygen is really stealing the electron density away from the sulfur. And the other reason is the pi bonds are almost non-existent. They're really weak because of the difference in their size, of the size of the p orbitals on sulfur and oxygen. So sulfur trioxide is our amazing electrophile from the get-go. We don't have to worry about having to use some sort of a catalyst to turn this into an amazing electrophile. So we can just start by reacting this with benzene, our very first step. Benzene is our poor nucleophile. In sulfur trioxide, we already have our amazing electrophile. So the nucleophile attacks the electrophile. Sulfur already has the maximum number of electrons it can hold here, and so it ends up breaking one of those really weak pi bonds. The pi bond only takes a nudge to break anyway, because it was hardly there in the first place. So you end up with this benzene ring, and you could add the sulfur trioxide anywhere, because the benzene is symmetrical. I'm going to add it to the top. So you have the sulfur here. 2 of the double bonds to oxygen are still intact. One of them has turned into, this one has turned into just a single bond. And now that oxygen, which had only 2 lone pairs, now has 3 and a full negative charge. So let me actually do this. Full negative charge. And the electrons in benzene, these electrons here, that were shared between 2 atoms, those actually move to form this new bond here. Right? That's what this curved arrow is talking about. It's using those electrons to form that new bond. So now they're only on one of the carbons, and the other carbon lost its electrons, and it has that positive charge. Well, at this point, you might recognize the similarity between this reaction and bromination. Remember that after bromination, we also formed this intermediate with that positive charge. Right? We had our good electrophile, the benzene attacking it, and you form this positive charged intermediate here. Okay. So you could do that same thing here. You see the pattern. And so here we have that positive charge, which is allylic. And so you're going to have resonance. So you warn the world by drawing those brackets, and the true structure is not going to be any individual structure. It's going to be the average of all of them. The true structure will only ever be the average. None of these individual structures we're drawing exist. And the reason why we know we have resonance is because we have an allylic positive charge, a positive charge that's one atom away from an atom in a double bond. And what that means, to say that that has resonance, what that means is that that positive charge, remember, is an empty p orbital. And you know you have parallel p orbitals because of the pi bond there. So you have 3 parallel p orbitals, and so the electron gets to spread out. And resonance is a way to describe that spreading out in the Lewis structures. And so to describe that resonance, to draw the other resonance structure, you draw a curved arrow going from the pi bond toward the positive charge that it's allylic to. Now, not at the atom, but toward the bond there. And so everything else stays the same, but this one bond moves over, and now the atom at the bottom is missing electrons, so it has the positive charge. That positive charge is allylic to 2 pi bonds. It's allylic to the one we just made, but if the electrons move back, we just get the structure we already drew. It's also allylic to the one on the other side. And so what that means, again, is that you have these parallel p orbitals forming the pi bond there. This is an empty parallel p orbital, and so those electrons can flow over all of those atoms. And we can show that by drawing another resonance structure, taking the electrons in the pi bond and moving them over to form a new bond toward the positive charge. We draw another resonance arrow that's telling you, take the average of all of these things. The true structure is only the average of these. And we end up with everything else in the molecule exactly the same, but the pi bond moved. So these electrons were shared between those 2 carbons. Now they've moved, and so this carbon here is missing electrons and has a positive charge. So those are the 3 possible resonance structures for this molecule. And the one thing that I didn't draw in here that I did draw in the bromination reaction is the fact that all these carbons have a hydrogen to begin with. If we track that hydrogen now, that hydrogen was on this atom this whole time. The molecule is able to restore aromaticity by using a base to steal that hydrogen. And the electrons that are going to the hydrogen will reform the pi bond in the benzene ring. Remember that this resonance stabilized intermediate is called a sigma complex. That term comes up a lot on standardized tests like the MCAT or the PCAT or the DAT. So that's a sigma complex. And you reform the aromaticity of the benzene ring when a base comes in, and in this reaction, it's the other thing in the fuming sulfuric acid. We've already used the sulfur trioxide. It's the water that's going to come in and act as a base. The oxygen there is slightly negative. The hydrogens each slightly positive. You've got your lone pairs. And so this slightly negative oxygen comes in and steals this hydrogen. The electrons go back to reform the aromaticity. So you end up with the benzene ring, which now has its aromaticity back, and you have the sulfur with the 3 oxygens on it. And the one last thing to consider in this mechanism is that that oxygen on the SO3 there has a negative charge. Now it's not so bad. It's really not the most unstable negative charge because it is spread out through resonance with both of those pi bonds. It gets allylic to those and then to the whole ring. Right? It's allylic to all of those atoms have parallel p orbitals that the electrons are able to fly through, and so the negative charge gets really spread out. So it's pretty stable. but it would be even more stable if it weren't there. And so this H3O plus molecule that we make in that last step, we had water and it accepted an H plus, that is able to act as an acid and donate its hydrogen to the SO3 minus. Yeah. So each of those hydrogens is really slightly positive because they're bonded to oxygen, which is very electronegative, and the oxygen is especially electronegative because it's attracting electrons with its positive formal charge. So these are really like low-hanging fruit, and when this molecule swoops in, the negative charge easily picks off the hydrogen, and so you end up getting that molecule there. And sometimes you'll see that written as just your regular benzene ring, and you'll see it written as SO3H, just to save space and time. But either of those are both the same thing. So one more time to review what we did. You'd see the recipe as fuming sulfuric acid. Notice it puts what it does is it takes a benzene and it puts that SO3H onto the benzene ring. The principle was the same as what we did before. You have benzene, which is a very bad nucleophile. You combine it with an amazing electrophile. Once that's on the ring, you get the resonance stabilized sigma complex, and resonance is restored, the aromaticity is restored when a base swoops in this case water, and steals the hydrogen on the carbon that the electrophile added to. In this step, there was just one last proton transfer to get rid of the negative charge on that oxygen in the branch. And so that's the sulfonation of benzene.